Look around at the physical environment, at the materials you can touch, the air you breathe, the ground beneath your feet, and the stars scattered across the night sky, and you are witnessing a profound cosmic anomaly. According to our most thoroughly tested and robust scientific frameworks, everything you see should fundamentally not exist. In the opening moments of the universe, during the first fraction of a second following the Big Bang, energy crystallized into equal quantities of matter and antimatter. For every single particle of ordinary matter that burst into existence, an identical partner carrying an opposite charge and identical mass was born right alongside it. If the standard rules of particle physics played out without a hitch, every single one of those particles and antiparticles should have met, collided, and mutually destroyed one another in a vast, universe-wide annihilation event. The only remnant left behind in that cold, expanding cosmos should have been an endless ocean of structureless light, stretching outward forever into absolute darkness. There should have been no periodic table of elements, no chemistry, no biology, no stars, no galaxies, and certainly no conscious minds capable of looking up at the sky and wondering why things are the way they are. Yet, here we are, navigating a reality built entirely on a microscopic margin of error. For every billion pairs of matter and antimatter particles that annihilated each other in the furnace of the early universe, exactly one solitary matter particle managed to survive. That 1 in a billion surplus, a discrepancy so minuscule it would have looked like a rounding error to any hypothetical observer watching the dawn of time, constitutes the entirety of the physical universe. Every atom in every living creature, every planet, and every distant galaxy visible through our most powerful telescopes is constructed entirely from that fragile residue. Physicists often describe the matter-antimatter asymmetry problem as the deepest open question in all of science, but that label barely scratches the surface of its true strangeness. The real oddity is not simply that the question remains unanswered, but that the question is deeply personal. It concerns your own body, the sky above your head, and every physical object you've ever encountered. The grand philosophical inquiry of why there is something rather than nothing is actually a concrete physics problem with a precise numerical target. That target is the ratio of matter particles to photons, a measured value of roughly 6 parts in 10 to the 10th, a number confirmed both through the faint afterglow of the cosmic microwave background and through the observed abundances of light elements forged during Big Bang nucleosynthesis. That specific number had to originate from somewhere in the fundamental laws of nature. Deep beneath the rolling fields that straddle the border between Switzerland and France, near Geneva and the shadow of the Jura Mountains, the European Organization for Nuclear Research operates some of the most sensitive and precise scientific instruments ever constructed to track down the hidden origin of that number. This grand experimental campaign operates across 2 radically different frontiers. On one side stands the Large Hadron Collider, a massive 27-kilometer ring of superconducting electromagnets buried 100 meters underground, where proton beams are smashed together at velocities approaching the speed of light, generating collision energies reaching 13 trillion electron volts. These cathedrals of detectors watch for fleeting sprays of particles that flicker into existence and vanish within fractions of a nanosecond. On the other side, situated in a much quieter building near the perimeter of the CERN campus, known as the Antimatter Factory, researchers capture single atoms of antimatter inside complex electromagnetic bottles, interrogating them one quantum transition at a time to determine whether they are exact mirror images of ordinary matter, or if subtle flaws betray a hidden asymmetry in nature. During recent experimental runs, one of these facilities yielded a milestone that had been anticipated for decades, shifting our perspective on the subatomic world. The LHCb collaboration confirmed at a statistical significance of 5.2 standard deviations, well past the rigorous threshold required for a formal physics discovery, that baryons, the 3 quark particles that make up nearly all visible matter, behave fundamentally differently from their antimatter counterparts when they undergo decay. While this breakthrough does not single-handedly solve the great matter-antimatter puzzle, it opens an entirely new chapter in our investigation. forcing us to examine what this specific type of asymmetry actually means, where it originates, why it falls short of explaining the whole universe, and what deeper theoretical frameworks might lie beyond it. To appreciate the magnitude of this quest, we have to look back to the late 1920s when theoretical physics underwent a revolutionary shift driven purely by mathematical elegance. In 1928, Paul Dirac set out to write an equation that successfully reconciled quantum mechanics with Albert Einstein's theory of special relativity, two pillars of modern physics that had previously resisted being brought together. The resulting formula, now universally known as the Dirac equation, described the behavior of electrons with an unprecedented level of precision. However, the mathematics came packaged with an uncomfortable and surprising consequence. The equation demanded a second shadow solution, representing a particle with the exact same mass as the electron but carrying an opposite electric charge. Dirac initially speculated whether this mysterious shadow might represent the proton, the only other charged particle known at the time, but that idea quickly collapsed because protons are nearly 2,000 times heavier than electrons, whereas his equations strictly required the two particles to be identical in mass. Thus, Dirac was forced to predict the existence of an entirely new particle, an anti-electron, born not from experimental observation, but from the strict mathematical requirement that relativistic quantum mechanics remain internally consistent. The experimental confirmation arrived just a few years later in 1932, when Carl Anderson at the California Institute of Technology was photographing cosmic ray tracks inside a cloud chamber. He spotted a particle track that curved in the wrong direction within a magnetic field, possessing the mass of an electron but a positive charge. Anderson named this discovery the positron, earning himself the Nobel Prize in 1936 and providing the first physical glimpse of antimatter. Over the subsequent decades, a comprehensive picture emerged showing that every fundamental particle in nature has an antimatter counterpart, sharing the exact same mass, but holding opposite charge, along with inverted quantum numbers such as baryon number and lepton number. The antiproton was triumphantly confirmed at Berkeley in 1955, followed immediately by the antineutron. By the 1960s, it was clear that antimatter was not merely an isolated quirk of a single particle, but a fundamental structural feature of reality itself. Matter is invariably accompanied by a mirror image, and the laws of physics appeared to treat both sides with absolute symmetry. This foundational concept is codified as CPT symmetry, standing for charge conjugation, parity inversion, and time reversal, forming one of the most inviolable theorems in quantum field theory. Proved rigorously in the 1950s using the core assumptions of relativistic quantum field theory, the CPT theorem states that any physically consistent universe must remain completely invariant if you simultaneously swap all particles with their antiparticles, flip all spatial coordinates like looking in a mirror, and run the flow of time backward. The implications of this theorem for antimatter are strict and uncompromising. The mass of an antiproton must match the mass of a proton down to the last decimal place. The lifetime of a positron must equal the lifetime of an electron, and every spectral line of antihydrogen must align perfectly with those of ordinary hydrogen. Should any of these fundamental equalities ever fail experimental scrutiny, CPT symmetry would be violated, requiring a total overhaul of the standard model of particle physics, a paradigm shift as monumental as the historical transition from Newtonian mechanics to general relativity. Against this backdrop of profound theoretical symmetry, the cosmological reality we observe presents a jarring contradiction. The universe we inhabit is entirely devoid of naturally occurring bulk antimatter. Somewhere during the opening fractions of a second of cosmic history, a mysterious mechanism tipped the scales, creating significantly more matter than antimatter and shattering the perfect balance that Dirac's equations seem to demand. Uncovering the exact nature of that symmetry-breaking event remains the primary objective of the entire CERN research program. The theoretical roadmap for solving this mystery was laid out decades ago by Andrei Sakharov, a brilliant theoretical physicist who is equally remembered as a political dissident and a champion of human rights. In a remarkably visionary paper published in 1967, Sakharov outlined three strict conditions that must be satisfied if a universe starting from a perfectly symmetric state of equal parts matter and antimatter is to evolve into one dominated entirely by matter. The first requirement is baryon number violation, meaning there must exist physical processes capable of generating an unequal number of baryons and antibaryons without conserving the total baryon count. The second requirement is charge conjugation and combined charge parity violation, ensuring that the fundamental laws of physics treat matter and antimatter differently. Otherwise, any process that generates a surplus of baryons would be perfectly countered by an opposing process, creating an identical surplus of antibaryons, leaving the net balance unchanged. The third and final condition is a departure from thermal equilibrium, because in a system resting in a state of perfect thermal balance, every forward reaction and its reverse occur at identical rates, preventing any cumulative asymmetry from building up over time. The standard model of particle physics actually satisfies all three of Sakharov's conditions in principle. Baryon number can indeed be violated through complex quantum mechanical processes known as sphalerons, which operate in the electroweak sector and were discovered by Gerard T. Hooft in the 1970s. These processes convert baryons into leptons at high temperatures, and in the fiery crucible of the early universe, sphalerons were active enough to alter the baryon balance significantly. Furthermore, charge parity violation naturally exists within the standard model through the Kabibo-Kobayashi-Maskawa mixing matrix governing quark interactions, and non-equilibrium conditions certainly prevailed during the turbulent electroweak phase transition when the Higgs field settled into its vacuum ground state. The fatal flaw, however, lies not in the presence of these mechanisms, but in their quantitative scale. The amount of charge parity violation generated by the standard model's quark mixing mechanism produces a matter-antimatter asymmetry that falls short of the observed value by roughly 9 to 10 orders of magnitude. That is not a minor discrepancy, it is a failure of scale by a factor of billions. Additionally, the electroweak phase transition for a Higgs mass of 125 gigaelectron volts, as measured by the Large Hadron Collider in 1912, turned out to be a smooth crossover rather than the sharp first-order phase transition required to generate the cosmic asymmetry efficiently. Consequently, both major pillars of the standard model's attempted explanation fail by staggering margins, proving conclusively that new physics must exist beyond our current understanding. The burning question for modern science is what form that new physics takes, at what energy scales it operates, and how we can detect its subtle fingerprints. To chase down these elusive answers, researchers rely heavily on the Large Hadron Collider, the colossal circular machine engineered to recreate the extreme conditions that existed mere picoseconds after the Big Bang. Within its 27-kilometer subterranean tunnel, two counter-rotating proton beams travel at nearly the speed of light, maintained at a cryogenic temperature colder than interstellar space by baths of liquid helium. When these high-energy beams cross paths inside the massive detector caverns, the localized energy density simulates the conditions of the primordial cosmos. Among the four primary detectors monitoring these collisions, the one most intimately tailored to tackling the matter-antimatter puzzle is the Large Hadron Collider Beauty experiment, widely known as LHCb. This detector is specifically optimized to study particles containing the bottom quark, often referred to as the beauty quark, which decays via the weak nuclear force over a timescale of approximately 1.5 trillionths of a second. The bottom quark is unique because it is the heaviest quark that still decays slowly enough to let its host particle travel a measurable microscopic distance from its point of production before disintegrating, allowing scientists to cleanly isolate its decay products from the overwhelming background noise of the collision. The LHCb detector is built in the shape of a specialized forward wedge, featuring microvertex resolution capable of tracking particles down to micrometers, advanced ring imaging Cherenkov detectors for precise particle identification, and comprehensive calorimeter systems backed by muon stations. Utilizing this sophisticated setup, the collaboration analyzed the complete dataset collected during Run 2 of the Collider, spanning proton-proton collisions recorded between 25 and 28. In a landmark announcement, the collaboration revealed the first definitive observation of charge parity violation occurring within baryons. The specific particle under investigation was the lambda B0 baryon, a bound state consisting of one bottom quark, one up quark, and one down quark, which decays into a proton, a kaon, and a pair of pions. By comparing its decay rate against that of its antimatter counterpart, the anti-lambda B0 baryon, researchers measured a statistically significant asymmetry of 2.45%, reaching a certainty level of 5.2 standard deviations. This monumental result marked the first time that charge parity violation was ever confirmed in baryons, the very category of particles that make up nearly all the visible matter in our universe. While the observed asymmetry aligns with predictions derived from the Standard Model's quark mixing matrix, it once again underscores the fundamental limitation we face. The mechanism predicts an effect that is far too weak to account for the vast baryon asymmetry of the cosmos. Thus, while the discovery confirms that the theoretical road exists and can be mapped out in heavy baryons, it does not lead to the final destination we seek. The broader history of studying charge parity violation began long before the construction of modern colliders, tracing its roots back to a critical discovery made in July 1964 at Brookhaven National Laboratory. Researchers James Cronin and Val Fitch, working alongside colleagues James Christensen and Renee Turley, published a startling paper reporting that long-lived neutral kaons occasionally decayed into a pair of pions at a tiny rate of roughly 0.2%, a process that should have been strictly forbidden if charge parity symmetry were an absolute law of nature. The physics community initially met the announcement with widespread skepticism, prompting meticulous re-examinations, careful control checks, and eventual confirmation that cemented the finding as one of the most profound experimental breakthroughs of the 20th century, earning Cronin and Fitch the 1980 Nobel Prize in Physics. The neutral kaon system is constructed from strange quarks, where a kaon 0 represents a bound state of a down quark and an anti-strange quark paired with its charge conjugate anti-kaon 0. These two distinct states undergo continuous quantum mechanical mixing. Prior to 1964, prevailing theory held that the propagating states derived from this mixing were exact eigenstates of charge parity symmetry, where one state possessed a positive eigenvalue, allowing it to decay into two pions, while the other held a negative eigenvalue, forbidding that specific decay pathway. The discovery of long-lived kaons defying this restriction forced a profound reevaluation of subatomic physics. The theoretical resolution arrived 9 years later, in 1973, when Makoto Kobayashi and Toshihide Masukawa demonstrated that charge parity violation arises naturally within the framework of quantum mechanics if there are at least 3 distinct generations of quarks, because a 3-generation mixing matrix inherently contains an irreducible complex phase. At the time of their proposal, only 3 quarks were known to science, but the subsequent discoveries of the charm quark in 1974, the bottom quark in 1977, and the top quark in 1995 at Fermilab successfully completed the 3rd generation, fully validating their theoretical framework and earning them the 2008 Nobel Prize. Over the decades that followed, the resulting mixing matrix was rigorously tested across dozens of distinct particle systems, including kaon decays, B-meson decays, D-meson oscillations, and now beauty baryon decays. Every single measurement has proven consistent with the theoretical framework, yet every single measurement also reinforces the frustrating reality that this specific phase is orders of magnitude too weak to explain why our universe is filled with matter. This constitutes the enduring irony of modern particle physics. An elegant mechanism confirmed to extraordinary precision across multiple generations of experiments stubbornly refuses to account for the physical existence of anything we can observe around us. In contrast to the high-energy environment of the Large Hadron Collider, the Antimatter Factory, located a short distance away on the CERN campus, takes the exact opposite approach, relying on extreme deceleration rather than extreme acceleration. The antiproton decelerator operates as a conceptual mirror to the massive collider ring. Where the LHC drives particles up to blistering energies, the decelerator slows them down relentlessly until they crawl at velocities low enough to be captured, contained, and studied in absolute isolation. The process begins by firing a high-intensity proton beam onto a dense metal target, triggering a chaotic spray of secondary particles that includes a small population of antiprotons. These antiprotons are magnetically separated from the debris and injected into a storage ring where high-frequency radio fields slow their movement, while a sophisticated technique known as stochastic cooling continuously dampens their momentum spread. Sensitive electronic sensors detect any orbital deviations from ideal trajectories and apply real-time corrective kicks, maintaining a tight, well-behaved beam bunch. From there, the particles pass into an even more specialized ring called the extra-low energy antiproton ring, which strips away further momentum until the antiprotons reach energies around 100,000 electron volts, making them slow enough to be captured inside electromagnetic traps. Several collaborative experiments utilize these low-energy beams to pursue unique measurement strategies. The alpha collaboration constructs complete anti-hydrogen atoms, confining them within specialized magnetic minimum traps so they can perform high-precision laser spectroscopy. Another experiment, Asakusa, produces cold beams of anti-hydrogen to measure their hyperfine structure in field-free environments. Meanwhile, the base experiment isolates single antiprotons inside penning traps to compare their fundamental properties, such as charge-to-mass ratios and magnetic moments, directly against ordinary protons. Yet another project, G-bar, focuses on creating anti-hydrogen ions and cooling them sympathetically before releasing them to measure their freefall behavior under gravity. Synthesizing anti-hydrogen requires combining trapped antiprotons with positrons harvested from radioactive isotope sources. This union must occur under meticulously controlled, slow conditions to ensure that a fraction of the newly formed anti-atoms possess kinetic energies low enough to be captured. The magnetic traps used by alpha confine these anti-atoms through their intrinsic magnetic dipole moments, though the effective depth of the trap corresponds to a thermal energy limit of only about half a Kelvin, meaning the anti-hydrogen must be thoroughly cooled right at the moment of birth. While early runs yielded only a handful of trapped anti-atoms, the introduction of advanced sympathetic cooling techniques, such as laser cooling beryllium ions, housed in the same trap to draw away thermal energy through electrostatic interactions, revolutionized the throughput. Today, experiments like alpha routinely accumulate over 15,000 anti-hydrogen atoms in a matter of hours, transforming what was once an impossibly difficult specialty into a thriving field of precision atomic physics. Spectroscopy serves as the universal language atoms use to reveal their internal structural secrets. When a quantum system absorbs or emits a photon, the energy of that particle of light matches the exact gap between two quantized energy levels within the system, producing a unique spectral fingerprint dictated by the masses and charges of the constituent particles and governed by the laws of quantum electrodynamics. If CPT symmetry holds true, the spectral fingerprint of anti-hydrogen must match that of ordinary hydrogen with absolute perfection. Hydrogen happens to be one of the most exhaustively studied systems in scientific history. The transition between the ground state and the second energy level, driven by ultraviolet laser light at a wavelength of 243 nanometers, has been measured by researchers at the Max Planck Institute in Garching to a fractional precision surpassing 4 parts in 10 to the 15th. This extraordinary benchmark helps define fundamental constants like the Rydberg constant and tests quantum electrodynamics at the absolute limits of experimental capability. The alpha collaboration achieved a major milestone by first observing this specific transition in trapped anti-hydrogen, and subsequent precision spectroscopy of its hyperfine components yielded transition frequencies matching standard hydrogen predictions well within current experimental uncertainties. While this level of agreement confirms no violation of CPT symmetry at that scale, current antimatter spectroscopy remains about 7 orders of magnitude less precise than ordinary hydrogen studies. Upgrades incorporating advanced fluorescence detection, improved optics, and direct laser cooling are rapidly closing that gap. Laser cooling of antihydrogen allows researchers to slow the thermal motion of the atoms, drastically extending their interaction time with probing lasers and sharpening spectral lines. As these anti-atoms are chilled down into the microkelvin range, achieving measurements at the parts per trillion precision level within the coming decade becomes entirely plausible. Complementary efforts by experiments like Asakusa focus on ground-free hyperfine splitting, measuring the tiny energy shifts arising from the interaction between the antiproton's magnetic moment and the positron's spin. In ordinary hydrogen, this phenomenon produces the famous 21-centimeter spectral line utilized by radio astronomers to map the distribution of neutral gas across our galaxy. Measuring the exact equivalent frequency in antihydrogen provides one of the most sensitive available tests of CPT symmetry within the electromagnetic sector. Beyond atomic spectroscopy, physicists have long sought to answer a fundamental mechanical question. Does antimatter fall downward under the pull of gravity in the exact same manner as ordinary matter, or does it behave differently? General relativity dictates that all forms of mass and energy must follow identical geodesics in curved spacetime, upholding the equivalence principle, which states that inertial mass and gravitational mass are permanently identical. However, Einstein formulated general relativity long before antimatter was discovered, meaning that extending the equivalence principle to antimatter has historically relied on a physical assumption rather than direct empirical proof. Over the decades, various speculative theoretical models suggested that if antimatter experienced gravitational repulsion from ordinary matter, it might provide a neat solution to the cosmic asymmetry problem by naturally segregating matter and antimatter domains during the early universe instead of letting them annihilate. Although such hypotheses faced severe theoretical objections regarding energy conservation, they could only be definitively settled through direct measurement of neutral antimatter because charged particles like bare antiprotons are far too susceptible to stray electric fields that easily overpower the feeble tug of gravity. The alpha-G apparatus resolved this long-standing mystery by trapping antihydrogen atoms inside a vertical magnetic cylinder and then slowly ramping down the magnetic fields to observe whether the neutral anti-atoms escaped upward or downward. Results published from these campaigns confirmed that antihydrogen falls downward toward the Earth, experiencing a gravitational acceleration consistent with standard gravity within experimental uncertainties. This conclusively demonstrated that antimatter does not fall upward, upholding the equivalence principle for antihydrogen to within current precision limits, with ongoing upgrades aiming to push that accuracy even further using laser-cooled atoms. Meanwhile, the BASE collaboration takes an entirely distinct route to testing fundamental symmetries by focusing on single antiprotons isolated inside ultra-precise penning traps. By combining strong uniform magnetic fields that force charged particles into circular cyclotron orbits with weak electric fields that restrain axial motion, researchers can measure both the cyclotron frequency and the Larmor precession frequency of a single trapped antiproton to determine its magnetic moment. CPT invariance demands that the magnetic G factor of an antiproton must match that of a proton in absolute magnitude. Measurements conducted by BASE have achieved breathtaking fractional precisions, reaching parts per billion and parts per trillion accuracy levels, making them the most rigorous tests of CPT symmetry in the baryon sector ever achieved. These high-precision constraints allow theorists to test generalized frameworks that parameterize any potential violations of Lorentz invariance, confirming that no deviations from standard physical law exist within our current experimental reach. To push these boundaries further, the BASE team has pioneered the development of portable antiproton traps, compact, battery-powered devices encased in heavy magnetic shielding, capable of holding a small population of antiprotons safely while being physically transported across the CERN campus or even to different geographic locations. Transporting antimatter between different laboratories or testing them against sidereal variations as the Earth rotates opens up entirely new avenues for detecting minute anomalies in fundamental symmetry. When exploring the theoretical landscape beyond the standard model, the most widely embraced framework for explaining the origin of matter-antimatter asymmetry is leptogenesis. This elegant hypothesis proposes that the cosmic asymmetry first emerged within the lepton sector and was subsequently converted into a baryon surplus by the electroweak sphalerons processes operating in the early universe. The mechanism, originally proposed in the mid-1980s, builds directly upon the seesaw mechanism for generating neutrino masses. The seesaw framework posits that the surprisingly tiny masses measured in ordinary neutrinos arise naturally from a mathematical seesaw balancing their Yukawa coupling against the exceptionally heavy mass of a hypothetical right-handed neutrino partner. If ordinary neutrinos possess masses on the fraction of an electron-volt scale, the natural output of the seesaw mathematics pushes the mass of these heavy sterile neutrino partners up toward the grand unification scale, where all fundamental forces are expected to merge. In the scorching temperatures of the primordial universe, these heavy neutrinos existed in thermal equilibrium, but as the cosmos expanded and cooled, they fell out of equilibrium and began to decay. Because their decay channels can produce leptons and Higgs bosons, or their antiparticles at differing rates whenever CP-violating complex phases are present in the Yukawa coupling matrix, a net lepton asymmetry accumulates. The electroweak sphalerons processes then convert roughly a third of that accumulated lepton surplus into the observed baryon asymmetry. The primary appeal of leptogenesis is its intimate connection to established discoveries, specifically the confirmation that neutrinos possess non-zero mass, validated by oscillation experiments recognized with the Nobel Prize. A universe where neutrino masses are governed by the seesaw mechanism and where heavy neutrino decays exhibit significant CP violation provides a natural explanation for the matter we see around us. The frustrating obstacle, however, is direct testability, because these heavy neutrinos reside at energy scales permanently beyond the reach of any foreseeable particle accelerator. Consequently, any empirical evidence for leptogenesis must be gathered through low-energy signatures, most notably by searching for charge parity violation in neutrino oscillations using long baseline detector facilities spanning thousands of kilometers across the globe. An alternative framework, known as electroweak baryogenesis, attempts to generate the baryon asymmetry closer to home, placing the critical phase transition right near the electroweak scale where modern colliders can actively search for new physics. This mechanism demands that the electroweak phase transition must be strongly first order, meaning the Higgs field undergoes a sharp, discontinuous jump into its vacuum state, nucleating expanding bubbles that collide and churn the surrounding plasma. Additionally, it requires extra sources of charge parity violation acting near the advancing bubble walls where the asymmetry is forged. Although the discovery of the Higgs boson closed off the simplest versions of this scenario within the standard model, extended Higgs sectors and supersymmetric models keep the possibility alive, leaving experimentalists to search for telltale gravitational wave echoes that might have been rippled across spacetime during those primordial bubble collisions. As experimental facilities continue to push the boundaries of energy, precision, and control, the investigation into why anything exists at all remains one of the greatest intellectual adventures in human history, bridging the most abstract realms of quantum theory with the tangible reality of our physical existence. The pursuit of answers regarding the fundamental asymmetry of our universe ultimately stretches beyond the confines of terrestrial laboratories, reaching out into the cold expanses of deep space where the earliest echoes of cosmic history remain preserved. While particle accelerators smash protons together at energies mirroring the universe's first picoseconds, and antimatter factories trap fragile antiatoms in magnetic bottles, cosmologists study the faint, ancient light that washes over us from every direction in the sky. The cosmic microwave background acts as a pristine thermal photograph of the infant cosmos, retaining tiny temperature fluctuations that reflect the exact density variations and particle distributions present long before the first stars ignited. Within these subtle patterns of hot and cold spots, astronomers read the primordial tally of matter and radiation, confirming that the ratio of survivors from the ancient annihilation event remains universally consistent across observable space. This cosmic consistency suggests that the mechanism responsible for tilting the balance of reality was not a localized anomaly, but a fundamental property woven into the fabric of physical law from the very beginning. To understand how theoretical physicists attempt to model this primordial tilting, one must venture into the complex mathematics of grand unified theories, frameworks that seek to merge the strong nuclear force, the weak nuclear force, and electromagnetism into a single, elegant mathematical description. At the immense energy scales that prevailed during the first fleeting fractions of a second after the Big Bang, these three distinct forces lose their individuality, operating as a unified interaction governed by a single coupling constant. Within such grand unified frameworks, the strict conservation laws that govern our everyday world, such as the separate preservation of baryon number and lepton number, naturally break down. Heavy hypothetical particles predicted by these theories can decay through pathways that transform quarks directly into leptons or antiquarks, providing the exact violation of baryon conservation that Andrei Sakharov identified as an absolute prerequisite for generating a matter surplus. As the universe expanded and cooled, these grand unified symmetries spontaneously broke, freezing out distinct forces and leaving behind the asymmetric residue that now constitutes every planet, star, and living organism. Yet, translating these sweeping theoretical concepts into verifiable predictions remains one of the greatest hurdles in modern physics. The energy scales associated with grand unification typically reside near 10 to the 16th gigaelectron volts, a realm completely inaccessible to human-made colliders like the Large Hadron Collider, which maxes out at a mere 13 tera electron volts. Because direct probing of these ultra-high energy regimes is impossible, researchers must rely on precision low-energy measurements and indirect astrophysical observations to hunt for ghosts of the high-energy past. For instance, grand unified theories frequently predict that protons are not entirely stable, but should eventually decay into lighter particles like positrons and pions over unimaginably long lifetimes, often exceeding 10 to the 34th years. Enormous underground detectors, such as Super-Kamiokande in Japan and its successor Hyper-Kamiokande, spend years watching massive vats of ultra-pure water, waiting for the faint flash of Cherenkov radiation that would signal the spontaneous death of a single proton. To date, no such decay has ever been observed, pushing the theoretical lower limit on proton lifetimes ever higher and forcing theorists to constantly refine or discard their favorite grand unified models. Simultaneously, the quest to understand antimatter has fostered remarkable technological innovations that stretch far beyond the walls of fundamental physics laboratories. The techniques developed to trap, cool, and manipulate fragile antiprotons and antihydrogen atoms have directly cross-pollinated into other scientific disciplines, most notably medical imaging and quantum information science. The methods used for stochastic cooling and particle beam confinement in CERN's decelerator rings share foundational engineering principles with particle therapy facilities utilized in advanced cancer treatments, where precision beams of protons or carbon ions are steered with millimeter accuracy to destroy deep-seated tumors while sparing healthy surrounding tissue. Furthermore, the handling of positrons, the antimatter counterparts of electrons, forms the operational core of positron emission tomography scanners used daily in hospitals worldwide to diagnose neurological disorders and monitor metabolic activity. In this unexpected way, the esoteric study of why antimatter vanished from the universe has yielded practical tools that touch human lives on a daily basis. Back at the cutting edge of theoretical inquiry, researchers are also exploring whether the solution to the matter-antimatter asymmetry might involve entirely new types of fields and particles that interact with normal matter only through gravity or very feebly through the weak force. Dark matter, which makes up roughly 85% of the total matter in the universe, shares a conceptual kinship with the baryonic asymmetry problem because both phenomena point to significant gaps in the standard model. Some theoretical models propose dynamic links between the dark sector and the observed matter surplus, suggesting that the same primordial processes that generated dark matter particles may have simultaneously influenced the survival rate of ordinary baryons. Exploring these portals requires a multi-pronged scientific strategy. combining underground direct detection experiments shielded from cosmic rays, astrophysical surveys mapping the large-scale distribution of galaxies, and high-precision laboratory tests of fundamental constants. As researchers look toward the future, the global physics community is actively designing the next generation of particle colliders capable of probing even deeper into the subatomic landscape. Proposals such as the Future Circular Collider envision a gargantuan 90-kilometer ring tunnel buried beneath the Swiss countryside, designed to push collision energies far beyond current thresholds and generate unprecedented quantities of heavy quarks and electroweak bosons. Coupled with ongoing refinements at the Antimatter Factory, where initiatives like laser-cooled anti-hydrogen beams and portable traps are opening up new experimental domains, science is steadily closing the net around the elusive mechanisms that shaped our existence. Whether the ultimate answer lies in the subtle quantum phases of elusive neutrinos, the explosive dynamics of primordial bubble walls, or entirely unforeseen principles of physics yet to be discovered, the journey to decode our cosmic origins remains an enduring testament to human curiosity and the drive to understand why there is something rather than nothing. As the scientific community pushes the boundaries of what can be observed, measured, and theorized, the investigation into the matter-antimatter asymmetry expands beyond high-energy colliders and low-energy traps into the complex realm of neutrino oscillations and the subtle properties of the PMNS mixing matrix. Neutrinos, long dismissed as ghostly, nearly massless spectators in the subatomic theater, have emerged as central figures in the grand narrative of cosmic origins. Unlike quarks, which interact via all four fundamental forces, neutrinos experience only the weak nuclear force and gravity, making them notoriously difficult to detect. Yet, it is precisely this elusive nature that makes them prime candidates for unlocking the secrets of the early universe. The discovery that neutrinos oscillate, meaning they spontaneously transform from one flavor to another as they travel through space, proved unequivocally that these particles possess a small but non-zero mass. This revelation immediately revitalized theoretical models like leptogenesis, providing a natural bridge between the microscopic world of subatomic mixing and the macroscopic asymmetry of the cosmos. Within the framework of neutrino oscillations, physicists look for evidence of charge parity violation in the lepton sector, utilizing massive long baseline experiments where intense beams of muon neutrinos or antineutrinos are generated at particle physics laboratories and fired through hundreds or even thousands of kilometers of Earth's crust toward distant underground detectors. Facilities such as is the Deep Underground Neutrino Experiment, currently under construction in the United States, and the Hyper-Kamiokande detector in Japan, represent the pinnacle of this experimental endeavor. By comparing the oscillation probabilities of neutrinos versus antineutrinos over vast baselines, researchers aim to determine whether nature treats leptonic matter and antimatter with the same subtle bias observed in the quark sector. If the PMNS matrix harbors a sufficiently large charge parity violating phase, it would provide crucial empirical support for the leptogenesis hypothesis, demonstrating that the asymmetry of the universe was born first among leptons before being reprocessed into the baryon surplus that forms everything we see today. Simultaneously, astrophysicists are scanning the cosmos for direct evidence of primordial antimatter that might have survived the initial annihilation era, tucked away in distant pockets of the universe where matter and antimatter domains were somehow segregated before they could destroy one another. The alpha magnetic spectrometer, installed on the exterior of the International Space Station, serves as a premier cosmic ray detector operating above the filtering interference of Earth's atmosphere. By analyzing the composition of high-energy cosmic rays streaming from deep space, AMS-02 searches for rare antiparticles such as antihelium nuclei or heavier antinuclei, which could signify the existence of distant stellar nurseries or galaxies composed entirely of antimatter. While the overwhelming majority of detected cosmic rays consist of ordinary matter, the discovery of even a single confirmed antihelium nucleus originating outside our solar system would shatter prevailing cosmological assumptions, forcing a radical reevaluation of how matter and antimatter interacted during the inflationary epoch. The challenge in such astrophysical searches lies in distinguishing genuine, primordial antimatter from secondary antiparticles generated locally through high-energy collisions between ordinary cosmic rays and the interstellar medium. Advanced particle identification techniques, combined with precise modeling of galactic propagation, allow researchers to parse these signals, turning the orbital laboratory into a vital outpost for observational cosmology. To comprehend the theoretical underpinnings that connect these diverse experimental efforts, one must examine the intricate topological features of quantum field theory, particularly the behavior of quantum anomalies and vacuum transitions in gauge theories. In the Standard Model, classical conservation laws are occasionally broken by quantum mechanical effects at high energies or temperatures, a phenomenon known as an anomaly. The electroweak Phaleron transitions represent a prime example of this behavior, where topological fluctuations in the gauge fields allow the system to tunnel between distinct vacuum states that differ in their net baryon and lepton numbers. In the scorching heat of the early universe, these transitions occurred at a rapid rate, wiping out any pre-existing baryon asymmetry unless specific dynamic conditions prevented the reverse processes from keeping pace. Understanding the exact dynamics of these topological transitions requires advanced computational techniques, including lattice quantum chromodynamic simulations executed on some of the world's most powerful supercomputers. These simulations model the behavior of quarks and gluons on a discrete space-time grid, allowing theorists to calculate transition rates, phase boundaries, and thermodynamic properties that cannot be solved using traditional paper and pencil mathematics. Through these computational windows, researchers test hypotheses regarding the nature of the electroweak phase transition, exploring whether additional scalar fields or supersymmetric partners could alter the dynamics sufficiently to make the transition strongly first order, thereby satisfying Sakharov's third condition in a manner that the standard Higgs sector fails to achieve. Looking toward the horizon of experimental particle physics, planning is already underway for future facilities designed to supersede the Large Hadron Collider and push the frontiers of energy and luminosity to unprecedented extremes. The proposed future circular collider concept envisions a monumental 90-kilometer ring tunnel situated beneath the Franco-Swiss border near Geneva, engineered to achieve proton-proton collision energies reaching 100 tera-electron volts, alongside dedicated modes operating as an intense electron-positron Higgs and electroweak factory. Such a machine would produce staggering quantities of heavy quarks, tau leptons, and electroweak bosons, enabling precision measurements of rare decay channels that are completely inaccessible with current instrumentation. By measuring these decay rates with extreme accuracy, physicists hope to detect tiny deviations from standard model predictions, so-called virtual quantum effects, where heavy, undiscovered particles briefly flicker into existence during a decay process before disappearing. These subtle quantum fingerprints could reveal the presence of new physics operating at mass scales far beyond the direct kinematic reach of the collider itself, providing indirect clues about the underlying forces that govern the creation of the universe during its first picoseconds. The synergy between these massive accelerator projects and precision low-energy experiments creates a comprehensive, multi-front assault on the matter-antimatter puzzle. While colliders like the FCC and LHCb probe the high-energy interactions and rare decays of heavy quarks, the Antimatter Factory at CERN continues to refine its techniques for trapping, cooling, and interrogating antihydrogen atoms and single antiprotons with breathtaking precision. The recent technological leaps enabling laser cooling of antihydrogen and the development of portable antiproton traps demonstrate that low-energy antimatter physics is no longer limited by crude containment methods, but has matured into a precision science capable of testing CPT invariance and the gravitational behavior of antimatter to unprecedented decimal places. If a deviation is eventually discovered, whether in the magnetic moment of an antiproton, the spectral lines of antihydrogen, the free-fall acceleration of neutral antiatoms, or the charge parity violating phases of neutrino oscillations, it will signal the crumbling of the Standard Model's apparent completeness and herald a new era of fundamental physics, This relentless scientific endeavor ultimately reflects a deep philosophical truth about humanity's place in the cosmos. We are not passive observers looking out at a universe that happens to be structured in a particular way. We are the literal physical manifestation of a microscopic mathematical imbalance that occurred nearly 14 billion years ago. Every carbon atom in our DNA, every drop of water in our cells, and every electrical impulse firing across our neural pathways is constructed from that single surviving particle out of every billion that emerged from the primordial furnace. The fact that we can build 27-kilometer subterranean rings, trap single atoms of antimatter in magnetic bottles, and decode the thermal afterglow of the Big Bang to ask these questions is itself a staggering continuation of that ancient cosmic evolution. The matter-antimatter problem remains unsolved not because human ingenuity has fallen short, but because the answer requires us to probe the deepest, most well-guarded secrets of physical law, testing the boundaries of quantum mechanics, relativity, and cosmology. As each new experiment refines its measurements and each theoretical model pushes further into the unknown, science inches closer to resolving the ultimate mystery of why there is something rather than nothing, transforming an ancient cosmic accident into a fully understood chapter of physical reality. To truly comprehend the monumental scale of the inquiry surrounding the matter-antimatter asymmetry, one must look even further back into the primordial timeline, past the first fraction of a second, straight into the fiery, turbulent epoch known as cosmic inflation. Before the universe experienced the hot Big Bang as we conventionally understand it, space itself underwent an incomprehensibly rapid and exponential expansion, driven by the potential energy of a hypothetical scalar field known as the inflaton. This inflationary period stretched the fabric of space by a factor of at least 10 to the 26th in a mere fraction of a blink, flattening its geometry, smoothing out irregularities, and diluting any pre-existing relics or unwanted topological defects that might have otherwise dominated the infant cosmos. Yet, inflation did more than just set the stage. It actively generated the seeds of all future structure through quantum fluctuations. As microscopic quantum jitters were violently stretched across macroscopic distances by the relentless expansion, they left behind microscopic density perturbations in the energy field. When inflation finally ended, the stored vacuum energy of the inflaton field decayed into a turbulent plasma of particles and radiation in a process known as reheating, effectively resetting the cosmic clock and initiating the hot Big Bang phase with a clean slate. It is precisely during this violent transition of reheating that many theoretical physicists believe the initial conditions for baryogenesis were forged, as the decaying inflaton energy converted into matter and antimatter fields under conditions far removed from thermal equilibrium, setting the stage for the subtle symmetry-breaking events that would later dictate the fate of the physical world. The intricate dynamics of reheating and the subsequent evolution of the primordial plasma bring to light another fascinating layer of complexity: the potential role played by exotic topological defects born during phase transitions in the early universe. As the cosmos cooled from extreme temperatures, different regions of space underwent spontaneous symmetry breaking independently, occasionally failing to lock into the exact same vacuum state. Where these mismatched domains met, topological defects such as cosmic strings, magnetic monopoles, or stable domain walls could become trapped in the fabric of spacetime. Certain speculative cosmological models suggest that the violent collapse or decay of these topological defects could have created localized zones of extreme energy density and non-equilibrium conditions, providing the necessary environment to drive anomalous baryon number violating processes far more efficiently than standard thermal fluctuations would allow. While most forms of topological defects, such as magnetic monopoles, would overclose the universe if they existed in excessive numbers, a crisis famously resolved by the introduction of inflation itself, others might have played a fleeting yet decisive role in tipping the cosmic scales before vanishing entirely into the expanding void. Exploring these possibilities requires advanced theoretical modeling that bridges cosmology and particle physics, combining general relativity with quantum field theory to simulate how microscopic topological fluctuations can manifest as macroscopic asymmetries on a cosmic scale. Venturing deeper into the theoretical underpinnings of modern physics, researchers also look toward the vast and mathematically intricate landscapes of string theory and supersymmetric frameworks to find natural resolutions to the asymmetry problem. In conventional four-dimensional quantum field theory, explaining why the parameters of the standard model take the specific values they do, such as the exact masses of the quarks and leptons or the strength of the charge parity violating phases, often feels like tuning an extraordinarily complex instrument by hand, adjusting countless arbitrary dials to match experimental reality. String theory attempts to eliminate this arbitrariness by postulating that the fundamental constituents of nature are not zero-dimensional point particles, but tiny, vibrating strings of energy operating in a 10-dimensional spacetime. In these higher dimensional models, 6 of the spatial dimensions are compacted or curled up into intricate geometric shapes known as Calabi-Yau manifolds, and the specific shape of these hidden dimensions dictates the physical laws, particle masses, and coupling constants we observe in our familiar four-dimensional realm. Within the sprawling landscape of string theory solutions, which encompasses an estimated 10 to the 500 distinct vacuum states, different regions of the multiverse may possess entirely different physical laws and particle content. From this perspective, the apparent fine-tuning of our universe, including the exact ratio of matter to photons that allows conscious observers to exist, can be understood through an anthropic lens, suggesting that while other pockets of the multiverse may be completely sterile, devoid of matter, or governed by entirely different forces, we naturally find ourselves inhabiting one of the rare observational niches where the fundamental parameters conspired to permit the formation of chemistry, stars, and life. Yet, despite the conceptual elegance of the string landscape and higher dimensional models, theoretical physicists remain fiercely committed to finding empirical, testable pathways to confirm or refute these grand ideas, recognizing that physics must ultimately remain an experimental science rooted in measurable reality. This commitment drives the continuous refinement of low-energy precision tests, neutrino oscillation programs, and high-energy collider strategies, each designed to capture the faintest whispers of new physics before they are drowned out by background noise. At the heart of this endeavor is a profound appreciation for the interconnectedness of seemingly disparate phenomena. The tiny mass of a neutrino measured in a subterranean detector in Japan, the precise magnetic moment of a single trapped antiproton in a Geneva laboratory, the subtle gravitational acceleration of an antihydrogen atom falling inside a magnetic cylinder, and the ancient temperature fluctuations etched into the cosmic microwave background are not isolated curiosities. They are different pieces of the exact same grand puzzle. Each measurement acts as a constraint, narrowing the acceptable parameter space for theories of baryogenesis and pushing us closer to a unified understanding of physical law. Consider, for instance, the profound implications of uncovering even a minute violation of CPT symmetry, or the equivalence principle in antimatter systems. If an experiment at the Antimatter Factory were to definitively detect that an antihydrogen atom falls with a slightly different gravitational acceleration than ordinary hydrogen, or that the magnetic moment of an antiproton deviates from its matter counterpart by an amount exceeding theoretical uncertainties, it would immediately signal the collapse of local Lorentz invariance and point toward a breakdown of standard quantum field theory. Such a discovery would not merely solve a lingering technical anomaly. It would provide the first direct experimental window into Planck-scale physics, the domain where quantum mechanics and general relativity finally merge, and where space-time itself is hypothesized to dissolve into a fluctuating quantum foam. Theorists have developed robust frameworks, such as the Standard Model extension, to systematically catalog and constrain every conceivable form of CPT and Lorentz violation, ensuring that experimentalists have a rigorous mathematical language ready to interpret any deviation, no matter how small. Every time the precision of these low-energy antimatter measurements improves by another decimal place, another slice of the theoretical landscape is rigorously tested and verified, reinforcing the remarkable durability of our current understanding while simultaneously heightening the suspense for what might lie just beyond the next threshold of sensitivity. Simultaneously, the high-energy frontier continues to push outward, defying the immense engineering and financial hurdles required to construct machines of unprecedented scale. The discussions surrounding future colliders, whether circular proton-proton rings spanning nearly 100 kilometers or linear lepton colliders designed to study the Higgs boson with microscope-like clarity, reflect the stubborn human refusal to accept permanent ignorance regarding the origins of our physical reality. These facilities are designed not just to verify existing predictions, but to explore uncharted territories where new symmetries, undiscovered particle families, or hidden force carriers might reside. If supersymmetry is correct, and every known particle possesses a heavier, undiscovered partner waiting to be unlocked at higher collision energies, those supersymmetric partners could provide the exact extra sources of charge parity violation and non-equilibrium dynamics needed to make electroweak baryogenesis a viable reality. If dark matter particles interact with the visible sector through undiscovered portals, colliders, and underground direct detection experiments working in tandem may finally unmask them, revealing the hidden scaffolding that supports the visible universe. Reflecting upon this vast, multi-decadal scientific journey brings us back full circle to the fundamental truth of our existence. The universe is an improbable masterpiece built entirely from a rounding error. The fact that the cosmos did not end in a sterile, featureless bath of pure radiation, but instead evolved into a rich tapestry of swirling galaxies, heavy elements, complex molecules, and sentient minds rests entirely upon the narrowest of margins, that solitary surplus particle surviving out of every billion pairs created in the dawn of time. Every technological triumph, from the superconducting magnets of the Large Hadron Collider to the electromagnetic traps of the Antimatter Factory, represents humanity's collective effort to retrace the steps of that ancient cosmic anomaly and read the hidden history written into the very fabric of matter. As researchers continue to refine their instruments, push the boundaries of precision measurement, and develop deeper mathematical frameworks, they are not merely solving an abstract academic riddle. They are actively decoding the personal biography of the physical world. We are the direct descendants of that microscopic asymmetry, the living proof that the laws of nature, for all their strict symmetry and mathematical rigor, harbored a subtle, beautiful flaw, a flaw without which there would be no story to tell, no universe to inhabit, and no conscious observers to ask the enduring question of why anything exists at all. As we trace the cascading implications of the matter-antimatter asymmetry across the vast architecture of modern physics, the investigation inevitably leads us toward another profoundly subtle frontier, the search for permanent electric dipole moments in fundamental particles. According to the foundational symmetries of quantum mechanics, a fundamental particle such as an electron, a neutron, or a proton should not possess a permanent electric dipole moment unless both parity symmetry and time reversal symmetry, and by extension, charge parity symmetry, are fundamentally violated. In a universe governed by perfect charge parity invariance, the spatial distribution of a particle's internal charge must remain entirely symmetric along its spin axis, rendering its electric dipole moment identically zero. However, if new physics exists beyond the standard model, such as the supersymmetric extensions, multi-Higgs doublet models, or complex left-right symmetric theories invoked to explain the origins of neutrino masses and baryogenesis, it frequently predicts tiny, non-zero electric dipole moments that sit just beyond our current experimental threshold. Physicists around the globe are engaged in a relentless technological race to measure these infinitesimal charge asymmetries with breathtaking precision. Utilizing advanced atomic, molecular, and optical techniques, researchers trap clouds of heavy polar molecules or laser-cooled atoms inside ultra-stable magnetic and electric field shields, subjecting them to intense electromagnetic fields to search for the microscopic precession that would signal a non-zero electric dipole moment. Because these experiments are exquisitely sensitive to external magnetic noise, stray electrical currents, and thermal fluctuations, they require state-of-the-art laboratory environments buried deep underground or isolated on floating optical tables. A confirmed detection of a permanent electric dipole moment in an electron or a neutron would instantly provide the smoking gun that theoretical physicists have hunted for decades. Direct, unambiguous evidence of charge parity violation operating outside the cramped confines of the Standard Model's quark mixing matrix. Such a discovery would not only validate the theoretical frameworks required for successful baryogenesis or leptogenesis, but it would also open a transformative window into the ultra-high energy physics of the early universe without ever needing to build a particle collider the size of a galaxy. Simultaneously, the investigation into fundamental symmetries extends into the bizarre and fascinating world of purely leptonic atoms and exotic bound states, such as positronium and muonium. Positronium is a short-lived atom consisting solely of an electron and its antimatter counterpart, the positron, orbiting a common center of mass before they inevitably annihilate each other into a burst of gamma-ray photons. Because positronium contains no ordinary nucleons, it serves as an ultra-clean laboratory for testing quantum electrodynamics and probing discrete symmetries completely free from the complex strong force interactions that complicate measurements involving protons and neutrons. Similarly, muonium, a bound state formed by a positive muon and an electron, provides an ideal testing ground for precision spectroscopy and muon magnetic moment determinations. The anomalous magnetic moment of the muon has captured intense global attention in recent years, particularly following high-precision measurements from facilities like Fermilab and the former Brookhaven experiment, which consistently hint at a persistent, statistically significant discrepancy between experimental observations and the rigorous theoretical predictions of the Standard Model. If confirmed, this muon anomaly would point directly toward undiscovered virtual particles, perhaps supersymmetric partners, dark photons, or new scalar fields, that subtly influence the quantum vacuum and alter the behavior of leptons. These leptonic systems, operating at the intersection of atomic physics and subatomic particle dynamics, provide an indispensable complement to the high-energy collisions at CERN and the low-energy antiproton traps of the Antimatter Factory, weaving a dense, interconnected web of evidence that steadily hems in the remaining mysteries of the subatomic world. As we step back to survey this vast intellectual landscape, the true beauty of the scientific enterprise becomes strikingly clear. The matter-antimatter asymmetry problem is far more than an isolated numerical puzzle, or a technical footnote in the annals of cosmology. It is the central narrative arc of our physical reality. Every milestone achieved across these diverse research fronts, whether it is the confirmation of charge parity violation in beauty baryons by the LHCb collaboration, the high-precision spectroscopy of laser-cooled antihydrogen atoms in the alpha experiment, the exacting comparisons of antiproton and proton magnetic moments in base, or the theoretical exploration of leptogenesis and electroweak phase transitions, represents a deliberate methodical step toward decoding the deepest secrets of nature. We are navigating a universe built entirely on the fragile, improbable residue of an ancient cosmic catastrophe, where a tiny 1 in a billion surplus of matter managed to escape total annihilation and give rise to everything we can see, touch, measure, and comprehend. The journey from that chaotic, incandescent primordial soup to the conscious, inquiring minds capable of unraveling its history is an epic written in the language of quantum field theory, general relativity, and precision measurement. And as humanity continues to peer into the subatomic depths and scan the ancient light of the cosmic microwave background, we are not merely studying the universe from the outside. We are participating in the universe's ongoing effort to understand itself. To fully appreciate the vast theoretical web that connects these disparate experiments, we must also examine one of the most elegant and baffling companion puzzles in modern physics, the strong charge parity problem. While the weak interactions governed by the Kabibbo-Kobayashi-Maskawa mixing matrix exhibit charge parity violation, quantum chromodynamics, the quantum field theory describing the strong nuclear force binding quarks together via gluons, allows for a theoretical term in its mathematical Lagrangian that should, by all rights, violate charge parity symmetry on a massive scale. If this term were free to take any arbitrary value permitted by the mathematics, neutrons would possess a permanent electric dipole moment millions of times larger than any experimental upper limit ever recorded by sensitive laboratory instrumentation. The fact that the neutron electric dipole moment has consistently measured out to be zero, or at least vanishingly small beyond our current ability to detect, is known as the strong charge parity problem. It represents a profound unnaturalness in the standard model, like a glaring sign that a crucial piece of the theoretical puzzle is missing. The most widely accepted solution to this riddle was proposed in the late 1970s by Roberto Peccei and Helen Quinn, who introduced a dynamic global symmetry that, when spontaneously broken, gives rise to a brand new pseudo-Nambu-Goldstone boson, known as the axion. Not only does the Peccei-Quinn mechanism elegantly force the troublesome charge parity violating term in quantum chromodynamics to cancel out dynamically, solving the strong charge parity problem with breathtaking mathematical economy, but the axion itself emerged as a premier candidate for dark matter. The invisible, ultralight axions drifting silently through the cosmos in staggering abundance could account for the missing 85% of matter in the universe, weaving together the mystery of the strong force, the enigma of dark matter, and the architecture of the early universe into a single cohesive narrative. Laboratories around the world, from resonant microwave cavity experiments like the Axion dark matter experiment to sophisticated optical interferometers, are now actively hunting for the faint conversion of axions into detectable photons when exposed to intense magnetic fields, adding yet another critical front to the global quest for physics beyond the standard model. The convergence of these distinct theoretical threads, neutrino masses, leptogenesis, electroweak baryogenesis, axions, and high-energy collider anomalies, reveals a deep underlying unity in the physical laws governing our universe. Every anomaly investigated at CERN, every precision measurement executed in the quiet rooms of the Antimatter Factory, and every ancient photon captured from the cosmic microwave background represents a vital coordinate on a map guiding us toward a comprehensive theory of quantum gravity and cosmological origin. As experimental techniques continue to evolve, incorporating quantum logic spectroscopy, laser-cooled antiatoms, portable magnetic traps, and multi-kilometer baseline neutrino detectors, the margin for hidden errors shrinks, forcing nature to reveal its deepest secrets. The journey from the searing, symmetrical chaos of the first fraction of a second after the Big Bang to the complex, matter-dominated cosmos we inhabit today is a testament to the power of human intellect and empirical inquiry. We stand as the conscious witnesses of a miraculous cosmic surplus, living proof that the universe's most consequential characteristic was not its vast, empty darkness, but the single, improbable survivor out of every billion colliding particle pairs that dared to remain, crystallizing into the stars, the planets, and the minds that look up to ask why anything exists at all. To push our exploration of the matter-antimatter asymmetry even further into uncharted territory, we must examine a phenomenon that sounds like science fiction, but is rooted in rigorous laboratory testing, namely the theoretical possibility of neutron-antineutron oscillations. While most experiments focus on decays or delicate atomic spectroscopy, neutron-antineutron oscillation proposes something far more radical, suggesting that a neutral baryon can spontaneously transform directly into its own antimatter counterpart without any intermediate decay products. According to certain extensions of the standard model, particularly those associated with grand unification and supersymmetric models that violate baryon number by 2 units, a free neutron drifting through a magnetically shielded vacuum chamber could occasionally morph into an antineutron. If that antineutron subsequently collides with the walls of its container or with surrounding ordinary matter, it triggers an instantaneous, highly energetic annihilation event, releasing pions and gamma rays that can be detected with absolute precision. Experimental searches for this bizarre quantum transition require massive, ultra-clean detectors shielded from the Earth's ambient magnetic field, because even a minuscule magnetic field disrupts the delicate quantum coherence required for the oscillation to occur. The upper limits established by these underground facilities have already pushed the characteristic oscillation time well beyond hundreds of seconds, providing tight constraints on the energy scales where grand unified symmetries must break down. If neutron-antineutron oscillations were ever definitively observed, it would not only confirm one of Sakharov's core conditions in the most direct manner imaginable, but it would also provide a vital clue pointing toward the specific high-energy mechanisms that governed the birth of baryonic matter in the first fraction of a second of cosmic history. Shifting our focus from the subatomic transformation of neutrons to the grand cosmological theater, researchers also investigate whether primordial magnetic fields generated during the inflation era could have played a decisive role in sorting matter and antimatter before annihilation could sweep them away entirely. During the turbulent phases of the early universe, plasma dynamics and phase transitions could have amplified tiny seed magnetic fields into macroscopic structures permeating the cosmos. Some theoretical models suggest that these intense primordial magnetic fields interacted differently with charged particles and antiparticles, creating localized pressure gradients or hydrodynamic barriers that temporarily segregated matter-rich domains from antimatter-rich domains, delaying complete annihilation and allowing small local surpluses to persist and grow. While standard inflation tends to smooth out magnetic fields along with everything else, generation mechanisms operating during reheating or at the electroweak phase transition can inject new magnetic energy into the cosmic plasma. Detecting the lingering relics of these primordial magnetic fields through their subtle imprints on the polarization of the cosmic microwave background or through the gamma-ray signatures of distant blazars provides another independent observational channel for reconstructing the physical conditions of the very early universe. Every measurement of intergalactic magnetic fields brings us closer to understanding whether macroscopic spatial sorting played any supporting role alongside microscopic CP violation in ensuring that our corner of the universe remained purely matter-dominated. Another fascinating dimension of the quest to understand our origins involves the search for sterile neutrinos, hypothetical particles that interact with the known universe solely through gravity and perhaps through extremely feeble mixing with active neutrinos. Unlike the three standard flavors of neutrinos that participate in weak nuclear interactions, sterile neutrinos would possess no standard electroweak charges, making them exceptionally difficult to detect directly. Yet their presence could elegantly resolve several of the most stubborn anomalies in modern physics, including the persistent short baseline neutrino oscillation anomalies reported by various experimental collaborations over the years, as well as providing a natural candidate for dark matter. Within the framework of extended seesaw mechanisms, these sterile neutrinos can span a massive range of mass scales, from the ultralight realms relevant to cosmology up to the near-Planckian masses required by traditional leptogenesis. If intermediate mass sterile neutrinos exist in the mega-electron-volt or giga-electron-volt range, they could potentially be produced in rare meson decays at high-energy colliders, or searched for through precise kinematic measurements in nuclear beta decay experiments. Uncovering a sterile neutrino would fundamentally rewrite our understanding of the lepton sector, providing the missing heavy partners that drive the seesaw mechanism, and validating the deep theoretical connections between neutrino mass generation and the ultimate creation of the matter-antimatter asymmetry. As we consider the sheer breadth of these complementary investigations, ranging from neutron-antineutron oscillation searches and primordial magnetic field studies to sterile neutrino hunts, high-precision atomic spectroscopy of antihydrogen, and charge parity violation measurements in heavy baryons, it becomes evident that solving the matter-antimatter problem requires an unprecedented synthesis of particle physics, astrophysics, and cosmology. No single experiment can provide the entire answer. Instead, progress depends on weaving together tight constraints from dozens of independent scientific fronts. Every time an experimental collaboration pushes a measurement down by another decimal place or a theoretical framework successfully predicts a subtle quantum anomaly, our collective picture of the universe's first second sharpens into greater focus. We are living through a golden age of fundamental physics, where centuries of theoretical speculation are finally meeting the rigorous standards of empirical verification, transforming the deepest mystery of existence into an open book waiting to be fully read. To delve even deeper into the quantum mechanics that govern the birth of the universe, we must examine the subtle role of quantum entanglement and coherence during the earliest moments of pair production. When energy transformed into matter and antimatter in the primordial soup, particles and their corresponding antiparticles were born as entangled pairs, sharing a unified quantum state that dictated their properties until an interaction broke that fragile link. In a dense, high-temperature thermal bath, these newly minted particles experienced constant collisions with surrounding radiation and plasma, causing rapid decoherence that separated the entangled partners and allowed individual reaction pathways to proceed independently. Theorists studying non-equilibrium quantum field dynamics investigate whether subtle coherence effects or quantum anomalous transport phenomena could have temporarily protected certain particle configurations from immediate annihilation, providing a microscopic window for asymmetry to accumulate before thermalization erased the trace. Simulating these complex, real-time quantum dynamics requires pushing computational physics to its absolute limits, utilizing lattice gauge theories to model how quantum fields behave far from equilibrium under extreme conditions that can never be fully recreated in a terrestrial laboratory. Beyond the quantum realm, the macroscopic distribution of matter in the visible universe offers another crucial piece of observational evidence for testing theories of early universe baryogenesis. By mapping the large-scale structure of galaxies and galaxy clusters through extensive astronomical surveys, cosmologists study baryon acoustic oscillations, the fossilized sound waves frozen in the distribution of matter when the primordial plasma combined into neutral atoms. These cosmic ripples serve as a precise standard ruler, allowing researchers to measure the expansion history of the universe and verify that the total amount of baryonic matter calculated from cosmic microwave background anisotropies matches the visible census of stars, gas clouds, and galaxies. Any discrepancy between these measurements would hint at unseen baryonic reservoirs or exotic modifications to gravity, providing a vital consistency check on the numerical target that any successful theory of matter-antimatter asymmetry must ultimately explain. The interplay between these vast cosmic structures and the subatomic physics of quarks, leptons, and gauge bosons demonstrate how the smallest quantum fluctuations are inextricably linked to the largest visible architectures in the cosmos. As experimental techniques continue to advance across multiple independent disciplines, the global scientific community edges closer to unraveling the deepest mysteries of physical law. Whether through the high-energy particle sprays of collider detectors, the ultra-cold electromagnetic traps of the Antimatter Factory, the long baseline oscillations of underground neutrino facilities, or the precise cosmological mapping of ancient light and large-scale structures, every new data point acts as a vital constraint on the architecture of reality. The journey to understand why there is something rather than nothing remains an ongoing adventure of human intellect, transforming an ancient cosmic mystery into a fully comprehensible chapter of the physical world. During the earliest epochs, when the ambient temperature of the cosmos exceeded the mass thresholds of heavy particles, reactions creating and destroying those particles occurred in rapid, symmetric equilibrium. As the universe expanded and cooled, the available thermal energy dropped below the threshold required to spontaneously forge massive particle-antiparticle pairs from pure radiation. At that critical juncture, the creation rate plummeted, and the remaining particles faced a stark choice between mutual annihilation and survival. In the case of ordinary matter and antimatter, if exact symmetry had prevailed down to the final freeze-out moment, the annihilation rate would have driven the surviving population down to an utterly negligible fraction, leaving behind a cold sea of photons far sparser than what we actually observe today. The fact that the surviving matter population stabilized at a ratio of roughly 1 particle for every billion photons points directly to an active, dynamic departure from symmetry during the active phase of freeze-out, requiring dynamic asymmetries in decay rates or scattering cross-sections that prevented the annihilation process from running to complete completion. Theorists, utilizing advanced kinetic Boltzmann equations, simulate these freeze-out epochs across millions of parameter variations. mapping out how different types of hypothetical particles and decay channels could leave behind the exact relic abundance we measure in the cosmic microwave background today. This delicate interplay between particle physics and thermodynamics is mirrored in the study of cosmic ray astronomy, where high-energy particles originating from distant astrophysical sources travel across intergalactic space before colliding with our upper atmosphere. Instruments deployed on high-altitude balloons, mountain peaks, and orbital spacecraft constantly monitor this invisible rain of radiation, searching for anomalous components that might betray hidden physics. Among the most intriguing targets in cosmic ray research is the search for secondary antiparticles, such as positrons and antiprotons, whose energy spectra can reveal whether exotic processes like decaying dark matter particles are contributing to the cosmic inventory. While many observed positrons can be accounted for by standard astrophysical mechanisms, such as pulsars acting as natural particle accelerators, lingering anomalies in high-energy positron fractions continue to spark intense debate among astrophysicists, keeping open the possibility that a portion of these antimatter particles stems from the very same hidden sectors responsible for the ancient matter-antimatter asymmetry. Disentangling standard astrophysical background noise from genuine signatures of new physics requires meticulous modeling of how cosmic rays propagate through the turbulent magnetic fields of our galaxy, diffusing across vast distances and interacting with interstellar gas clouds before they are finally captured by our detectors. Expanding our gaze from local galactic cosmic rays to the farthest reaches of the observable universe, high-energy neutrino observatories such as the IceCube detector buried deep beneath the Antarctic ice sheet offer another unique vantage point for probing fundamental symmetries. IceCube consists of a cubic kilometer of pristine glacial ice embedded with thousands of optical sensors designed to detect the faint blue flashes of Cherenkov radiation emitted when high-energy cosmic neutrinos crash into atomic nuclei within the ice. While the vast majority of these neutrinos originate from atmospheric interactions or solar fusion, a small subset possesses energies reaching into the peta-electron-volt regime, signaling an extragalactic origin. By tracing the arrival directions and energy profiles of these ghostly messengers, astrophysicists can probe extreme cosmic engines such as active galactic nuclei, gamma-ray bursts, and colliding black holes. Although neutrinos are notoriously difficult to link directly to baryogenesis without precise measurements of their mass hierarchy and mixing parameters, observing how high-energy neutrinos and antineutrinos behave across cosmic baselines provides an ultimate test of Lorentz invariance and CPT symmetry on a cosmological scale, ensuring that no hidden violations are lurking in the highest energy corners of the universe. The pursuit of these answers inevitably leads us to confront one of the most confounding puzzles in all of theoretical physics, the cosmological constant problem, which shares a deep conceptual boundary with the matter-antimatter asymmetry. When quantum field theory calculates the expected energy density of the vacuum by summing up the zero-point energy fluctuations of all known particle fields, the resulting theoretical value exceeds the observed dark energy density of the universe by a staggering factor of 10 to the 120th. This is widely considered the worst theoretical prediction in the history of science. Both the cosmological constant problem and the matter-antimatter asymmetry problem stem from our fundamental ignorance of how quantum mechanics behaves in the presence of gravity and extreme vacuum states. Many theoretical physicists suspect that a comprehensive solution to the matter-antimatter puzzle will not arrive in isolation, but will instead emerge as a natural byproduct of resolving the vacuum energy problem, perhaps through dynamical mechanisms that force the vacuum energy to relax to near-zero values, while simultaneously driving an early asymmetric expansion that favors matter over antimatter. Exploring these sweeping theoretical bridges requires pushing past the limits of conventional effective field theory, diving into speculative yet mathematically rigorous domains where space-time itself is treated as a dynamic, emergent phenomenon woven from deeper quantum entanglement networks. As we consider the sheer breadth of these theoretical frameworks and experimental efforts, it becomes abundantly clear that our understanding of physical reality is sitting on the cusp of a profound transformation. Every time a new data point is harvested from the high-energy collision sprays of the Large Hadron Collider, every time a single antiproton's magnetic moment is measured to an extra decimal place in the quiet halls of the Antimatter Factory, and every time an ancient photon from the cosmic microwave background is analyzed with higher fidelity, we are chipping away at the unknown. The fact that we are here to ask these questions, built from a fragile 1 in a billion residue of an ancient cosmic catastrophe, remains the most inspiring reminder of why scientific inquiry matters. We are the universe's way of thinking about its own birth, turning an accidental mathematical flaw into an enduring testament to human curiosity. We must examine the concept of hidden sectors and dark forces, which propose that the visible matter we can touch and measure is only a fraction of a much richer, more complex subatomic reality. While standard model particles interact via electromagnetism, the weak force and the strong force, modern theoretical frameworks increasingly suggest the existence of parallel gauge sectors populated by dark particles that do not feel these forces directly. Instead, these hidden sectors might communicate with ordinary matter through very rare, feeble portals, such as kinetic mixing between regular photons and hypothetical dark photons, or interactions mediated by ultralight scalar fields. Some advanced models of baryogenesis suggest that the asymmetry responsible for our existence was not generated within the familiar quarks and leptons of the standard model at all, but was instead forged in a secluded dark sector during the early universe, before being transferred over to the visible matter sector through portal interactions as the cosmos cooled. Exploring this hidden architecture requires ingenious experimental strategies, ranging from precision low-energy electron beam dump experiments searching for elusive dark photons, to ultra-sensitive detectors designed to catch the faint signatures of hidden particles, converting into standard photons inside intense magnetic fields. If such a dark portal were ever discovered, it would radically transform our understanding of particle physics, revealing that the matter-antimatter asymmetry we observe in our daily lives is merely the visible echo of a much grander hidden drama that played out across the entire cosmos during its fiery birth. To simulate and test these intricate theoretical landscapes, modern physicists are increasingly turning away from traditional pen and paper calculations and even conventional supercomputing, diving headfirst into the revolutionary paradigm of quantum simulation. Simulating the real-time, non-equilibrium quantum dynamics of fields during the electroweak phase transition or the chaotic moments of reheating involves mathematical complexities that quickly overwhelm classical computers, which struggle exponentially as the number of interacting quantum states grows. Quantum simulators, built from arrays of trapped ions, superconducting circuits, or ultra-cold atoms manipulated by laser beams, offer a direct hardware-level emulation of quantum mechanical systems. By mapping the behavior of quantum field equations onto controllable laboratory systems, researchers can observe how quantum entanglement, particle creation, and symmetry-breaking phase transitions unfold in real time under conditions that mimic the early universe. This emerging computational frontier allows theorists to test hypotheses about baryogenesis and topological defect formation with unprecedented fidelity, bridging the gap between abstract mathematical models and verifiable physical behavior. Simultaneously, the global astronomical community is preparing for a new generation of space-based observatories and ground-based telescopes designed to peer deeper into the infrared and microwave skies, searching for the most ancient signatures of cosmic inflation and reheating. Instruments such as next-generation cosmic microwave background polarization satellites aim to measure B-mode polarization patterns with exquisite precision. These swirling patterns in the ancient light act as a direct fingerprint of primordial gravitational waves generated during the inflationary epoch. Detecting these gravitational waves would not only confirm the theory of cosmic inflation with absolute certainty, but it would also provide crucial clues about the energy scale at which the universe underwent its most dramatic expansion phase, directly constraining the theoretical environments where baryogenesis and leptogenesis could have taken place. When combined with the high-energy data streaming from CERN and the ultra-low-energy precision measurements from the Antimatter Factory, These cosmological observations create a unified scientific framework where the smallest subatomic interactions and the largest structures in the universe are bound together by the same fundamental laws. Reflecting upon this vast multidisciplinary quest, it becomes evident that the pursuit of the matter-antimatter asymmetry is much more than an academic exercise in particle physics. It is the ultimate investigation into why reality has any structure at all. Every precision measurement of an antiproton's magnetic moment, every statistical confirmation of charge parity violation in heavy baryons, every long baseline neutrino oscillation anomaly, and every ancient photon captured from the edge of the observable universe represents a vital step toward completing our comprehension of physical law. We are standing at a unique crossroads in human history, equipped with the technology and the theoretical maturity to decode the very mechanics that rescued matter from total annihilation. The single, improbable surplus particle out of every billion that survived the dawn of time is the seed from which everything we know has grown. And as science continues to push the boundaries of what can be observed and understood, we inch ever closer to solving the deepest riddle of existence. We must turn our attention to the intricate mathematics of flavor physics and the Kabibo-Kobayashi-Maskawa matrix, exploring why its complex phases fall so drastically short of explaining the observed universe. The mixing matrix describes how quarks transform from one flavor into another via the weak nuclear force, and it accommodates a single, irreducible complex phase that introduces charge parity violation into quark decays. While this phase has been verified with extraordinary precision across decades of experiments studying kaons and B-mesons, and now reaffirmed in beauty baryons by the LHCb collaboration, its quantitative output is throttled by the mass hierarchies of the quark generations. Because the masses of the lighter quarks are so small compared to the electroweak scale, the mathematical combination of these mass differences, often referred to as the Jarlskog invariant, which measures the overall magnitude of charge parity violation in the standard model, evaluates to a tiny numerical value on the order of 10 to the minus 22. When this minuscule invariant is plugged into cosmological models of baryogenesis, it generates an asymmetry that is too weak by many orders of magnitude, proving that the quark sector alone cannot be the engine that drove the creation of our universe. This quantitative failure has driven theorists to look beyond the standard model toward extended frameworks, such as multi-Higgs doublet models or left-right symmetric theories, which introduce entirely new sources of charge parity violation that are decoupled from light quark masses and capable of supplying the massive asymmetry required by our existence. Parallel to these theoretical explorations in flavor physics, researchers are also probing the deep connections between cosmic inflation and the generation of matter through mechanisms known as Affleck-Dining baryogenesis. Proposed in the early 1980s by Ian Affleck and Michael Dine, this elegant framework utilizes supersymmetric extensions of the standard model to generate large baryon asymmetries during or immediately after inflation. In supersymmetric theories, every standard particle possesses a heavy bosonic or fermionic partner, including scalar partners to quarks and leptons known as squarks and sleptons. During the inflationary epoch, the potential energy of the universe can displace these scalar fields far from their zero-point vacuum values, imparting a large coherent field value that carries a net baryon or lepton number. As the inflaton field decays and the universe enters the reheating phase, these displaced supersymmetric fields begin to oscillate around their minimum energy states. Because the complex potential governing these fields contains charge parity violating terms, the oscillations naturally develop a rotational motion in complex field space, converting the initial potential energy into a dense surplus of real baryons or leptons before the fields eventually decay into ordinary particles. Affleck-Dining baryogenesis bypasses the severe suppression limitations of standard thermal leptogenesis because it relies on coherent classical field dynamics rather than slow freeze-out kinetics, making it one of the most powerful theoretical mechanisms for explaining how a massive matter surplus could be rapidly generated in the turbulent aftermath of cosmic inflation. To test these sophisticated supersymmetric and Affleck-Dining scenarios, The global experimental network relies heavily on the pursuit of precision measurements that can detect subtle deviations from standard model expectations. For instance, high-precision searches for rare lepton flavor-violating decays, such as a muon spontaneously transforming into an electron and a gamma-ray photon without emitting neutrinos, provide an exceptionally clean probe of new physics. In the standard model, neutrino oscillations prove that lepton flavors are not strictly conserved, but the rate of charged lepton flavor violation through neutrino mixing alone is absolute zero that is completely unobservable. If an experiment were to detect even a single charged lepton flavor-violating decay, it would serve as an unambiguous signpost pointing toward new high-energy physics, such as grand unified theories or supersymmetric extensions that mediate these rare transitions at measurable rates. Facilities around the world are currently upgrading their beamlines and detectors to push the sensitivity of these searches to unprecedented levels, ensuring that any hidden supersymmetric partners, or heavy sterile neutrinos, participating in flavor-changing processes, will reveal their presence through virtual quantum loops. As these experimental programs push forward, they are increasingly complemented by advances in computational cosmology and lattice field theory, which allow researchers to simulate the violent thermal histories of phase transitions with extreme numerical rigor. Simulating a first-order electroweak phase transition requires tracking the nucleation, expansion, and collision of microscopic vacuum bubbles across a multidimensional field space, capturing how charge parity-violating interactions operating at the expanding bubble walls can selectively reflect matter particles while absorbing or annihilating antimatter. These computationally intensive simulations demand the deployment of massive supercomputing clusters running continuously for months, solving complex quantum field equations on discrete space-time lattices to determine whether specific extensions of the Higgs sector can successfully generate the required baryon asymmetry without violating existing constraints from collider experiments. By comparing the predicted spectrum of gravitational waves generated by these violent bubble collisions against the sensitivities of planned space-based gravitational wave observatories, physicists open up an entirely new observational window into the early universe, allowing us to listen for the physical echoes of the phase transition that ultimately secured the survival of matter. The extraordinary convergence of these diverse scientific disciplines, from collider physics and low-energy antimatter traps to neutrino oscillation experiments, primordial gravitational wave astronomy, and advanced lattice simulations, we gain a profound appreciation for the unity of physical law. The matter-antimatter asymmetry problem is not merely a localized anomaly to be patched over with an ad hoc fix. It is a foundational diagnostic of our entire scientific worldview. Every precise measurement, every theoretical breakthrough, and every technological innovation brings us closer to comprehending how the universe engineered its own awakening. We are living proof of that ancient cosmic anomaly, standing at the culmination of a 14 billion-year journey from a searing symmetrical void to a complex, vibrant reality filled with stars, planets, and conscious minds capable of asking why anything exists at all. The recent milestones achieved across the global particle physics landscape, particularly the breakthroughs in coherent spin control of single antiprotons and dramatic leaps in antihydrogen production rates, offer a fitting continuation to our journey through the matter-antimatter puzzle. When the base collaboration successfully manipulated the quantum spin states of an isolated antiproton using precise radiofrequency fields inside a cryogenic penning trap, they effectively turned a piece of antimatter into a controllable quantum two-level system. Achieving phase coherence that lasted over 50 seconds allowed researchers to execute multiple Rabi oscillations, paving the way for hypersensitive magnetic moment comparisons that test fundamental symmetries with unprecedented exactness. This triumph of experimental control runs parallel to the developments at the ALPHA experiment, where introducing laser-cooled beryllium ions to draw away thermal energy through sympathetic cooling boosted antihydrogen accumulation rates by an order of magnitude. Gathering thousands of anti-atoms in mere hours transforms the study of atomic antimatter from a grueling exercise in statistical scarcity into a high-throughput precision science. enabling researchers to probe the optical and hyperfine spectral structures of antihydrogen with growing rigor. These experimental triumphs highlight a broader truth about the evolution of modern physics. Progress often relies on mastering extreme control over systems that naturally resist containment. Whether engineers are refining stochastic cooling loops in decelerator rings, designing portable magnetic traps capable of moving antiprotons between laboratories, or probing the gravitational fall rates of neutral antiatoms with rising accuracy, every technical barrier overcome brings us closer to isolating the minute flaws in nature's mirror. The overarching narrative remains deeply tied to our own physical existence, reminding us that the grandest cosmic questions are ultimately answered by manipulating the smallest, most fragile components of reality. As new strategic roadmaps for non-collider physics take shape and future facility upgrades loom on the horizon, the drive to decode the universe's most profound asymmetry continues to push human ingenuity into uncharted territory, ensuring that the mystery of why we are here remains one of the most compelling adventures of our time.